Hi, this is Professor Jamie Chan at California State University, Long Beach. In this video lesson today, we'll look at the end behaviors of polynomial functions. In particular, we're going to look at graphs of well-known monomials. Well, monomials are just polynomial functions of a single term. We're going to look at features that cannot appear on the graphs of polynomial functions. We're also going to look at the end behaviors of polynomial functions from the formula, meaning that what happens towards the positive end and negative end of the polynomial functions as x values gets really big and really small. I'm going to use correct notations to describe end behaviors of polynomial functions. It turns out that all polynomial functions follow or look somewhat like one of those 5 pictures shown here. These are graphs of monomials. For example, this first one is the graph of y equals x, which is a line. The second one here is y equals x squared, and that's the well-known parabola shape. The third one here is the picture of y equals x cubed. And the fourth one here is the picture for y equals x to the fourth. And the fifth one here is the picture for y equals x fifth. Notice that the picture for y equals x squared and the picture for y equals x to the fourth looks almost identical, having those upward opening parabola shape. On the other hand, the picture for x cubed and x to the fifth looks very similar as well, extending from the first quadrant to the third quadrant. As it turns out, is that the graph of p of x equals x to the nth has the same general shape as the graph of y equals x squared when n is even, and having the same shape as y equals x cubed when n is odd. However, as the degree n becomes larger, the graphs become flatter around the origin and steeper elsewhere. You can compare that by comparing y equals x squared and y equals x fourth. For example, if you look at the graph near the origin, you notice that the graph of x to the fourth is actually flatter near the origin than the graph of x squared. A similar phenomenon appears when you compare the graph of y equals x cubed and y equals x to the fifth. It is flatter near the origin for the x fifth function. Knowing the shape of these monomial functions helps us to understand the shape of the transformed version of those monomial functions. For example, if I note x cubed looks like this shape, then putting a negative sign in front has the effect of flipping or reflecting this graph around the y-axis. Another example is if I note the shape of the monomial for x to the fourth, which is this blue curve right here around the origin, then subtracting the 2 on the x variable has the effect of translating the graph 2 units to the right, and that allows us to get the red curve there. In the third example, if we know the graph of negative x to the fifth, which is the blue curve, then multiplying a 2 in front of it has the effect of stretching the curve, and then adding a 4 at the end has the effect of translating the monomial function up 4 units in the y direction. In general, we add and subtract these transformed monomial functions to get the general expression for the polynomial functions. And if we do that, we will get graphs of polynomial function looks like the following. These functions have the characteristics of being continuous and smooth. Graphs of continuous functions have no holes or breaks. A hole would look something like this, where you actually have to lift up your pencil and draw a hole and then continue your graph again. A break would look something like this, where you have to jump from one point to the next. Graphs of smooth functions have no cusp or corner. A cusp is something that locally looks like a V. A corner has the characteristic, if you were to draw a tangent line from the left-hand side and a tangent line from the right-hand side, they do not look the same, or they do not share the same direction. On the other hand, the cusp, if you were to draw a tangent line near the point of a cusp, then on the right and on the left should be exactly the same, and they both look like a vertical line. Next, let's formally define what a polynomial is. A polynomial is a function of the form that looks like the following, where n is the non-negative integer that denotes the degree of the polynomial, and an has to be non-zero, because if an is the coefficient that sits in front of the degree n monomial, if that is equal to 0, that means you do not have a degree n polynomial. You actually have the degree next to it, which is, in this case, could be n minus 1, if an minus 1 is non-zero. So these numbers a0 through an are called the coefficients of the polynomial. The number a0 is the constant term or the constant coefficient of the polynomial. It's really the coefficient for the monomial x to the 0th power, which we know any real number raised to the 0th power is equal to 1. And that's why we simply just get a0 there. The number an, which is the coefficient to the highest power, is called the leading coefficient. And the term that has the leading coefficient in it is called the leading term. Let's look at an example with all these terminology here. Here we're considering the polynomial 2 minus 3x plus 4x squared plus 10x to the 5th. Notice that we purposely write it in increasing order, where we start with the lowest power or degree all the way to the highest degree of this polynomial. This is a polynomial of degree 5 because 5 is the highest power that any monomial has. The constant coefficient is the one that has no x attached to it, which is 2 in this case. The a0 coefficient is the coefficient that's attached to the constant term, which would be 2. The a1 coefficient is the coefficient attached to the linear term, which is the x to the first power, and that's negative 3. And always remember to carry the correct sign with that, because the general formula uses plus sign everywhere. a2 is the coefficient for the quadratic term, which is 4 in this case. a3 is the coefficient for the x cubed term, which is missing in this polynomial, and that means a3 is equal to 0. For the same reason, a4 is also 0. a5 is the coefficient for the x to the 5th monomial, which is 10. There is no 6th degree or 7th degree monomial in this expression here, therefore a6 and a7 are both equal to 0. The leading coefficient is the coefficient that is attached to the highest degree, or the degree of the polynomial, which is 10. The leading term then would be 10x to the 5th. Next, let's look at the end behavior of polynomial functions. End behavior is a very useful tool for us to graph polynomial functions. And the way we look at it is by describing the behavior of the output as the input gets large in both directions, in both positive and negative directions. And the way we think about the input x gets large in both directions is the following. We say that x gets large in the positive direction if we start with 0 and then increase gradually to reach a very big number. So for example, we typically use 1 to 10 and then to 100, then to 1,000, eventually to 10 to a certain power that you're comfortable with. For example, I can say 4 here. Eventually, if you go far enough, this will go towards the infinity. The notation we use to denote this phenomenon or this behavior is x approaches infinity. Similarly, we can model the behavior of x getting large in a negative direction. We start with 0 as well and then decreases to the next bigger number, which is negative 1, then negative 10, negative 100, and then to negative 1,000, and eventually to negative 10 to some power. I'm here going to put 4 here. If you keep continuing on with this pattern, eventually this is going to go towards the negative infinity, and we denote this by x goes to negative infinity. So to describe the end behavior, we will look at what happens to the output, which is the y direction, as x goes to the positive infinity, and what happens to the y as x goes to the negative infinity. Well, what happens to the outputs when x goes to positive infinity? Well, let's look. If you start with 0, then the y value is 0. If you then move to 1, then the y value goes to 1, and then keep going. So what happens as x gets really large? The y value gets large as well, and then actually gets large in a positive direction. So y goes to the positive infinity as x goes to infinity. On the other hand, if x goes to the negative infinity, what happens to the y values? Well, again, we start with 0, and then we move to negative 1. Negative 1 would then correspond to a y value of negative 1 as well. Negative 10 would then correspond to a negative 10 for the y value. And keep going with this pattern, eventually we'll see that the y value reaches the negative infinity as x goes to the negative infinity. In the next example, let's see what happens to the y values as x gets large in the positive direction. If you start with the 0 and move to a bigger value of x, notice what happens to the y value there. It gets larger and larger and larger as x gets larger as well. So it seems to me that y goes to the positive infinity as x goes to the infinity. On the other hand, if the x value gets smaller or gets bigger in the negative direction, then what happens to the y value there? It also gets larger and larger to the positive infinity. So we say y goes to the positive infinity as x goes to negative infinity. And these are the end behaviors for this function. Now take a moment and try to see if you can figure this out yourself. Let's figure out the end behavior of this graph here and try to match it with one of those options. In this case, we notice that as x gets larger and larger in the positive direction, the y value gets smaller and smaller, or gets larger in the negative direction. So I can say that y goes to the negative infinity as x goes to the positive infinity. On the other hand, as x gets larger in the negative direction, the y value gets to the negative infinity as well. So I say y goes to the negative infinity as x goes to the negative infinity. And that corresponds to the option D here. If you didn't get the correct answer for the previous example, this is another chance for you to practice it again. If you got it previous time, great. Let's just make sure you can get it this time as well. Pause the video and try to do this yourself. Come back for answer. If you're still having trouble to see which way is the positive infinity, which way is the negative infinity, I suggest you label that on your graph here to indicate. The positive direction of the x-axis indicates the positive infinity here, and then you have the negative infinity on the other hand. The positive y direction eventually will go to the positive infinity, and this is going to be a negative infinity there. So now, as x gets larger in the positive direction, we look at what happens to the y value. It could actually get big for a while, right? In the beginning, it can do random things. It could go small, it could then get big in the positive direction, but eventually, this is what we mean by end behaviors, eventually it has to go down in a certain pattern all the way towards either positive or negative infinity. So in this case, it actually gets smaller and smaller and smaller and never returns. So I would say that the y goes to the negative infinity as x goes to positive infinity. On the other hand, if x gets large in a negative direction, in the beginning it can have some positive values and it actually dips down below the x-axis to get some negative x values, but eventually it's just going to reach all the way to the positive infinity. So I would say that y goes to the positive infinity as x goes to the negative infinity. And this matches with option B. In this next example, it gives you kind of a numerical aspect of how to determine the end behavior when the graph of the function is not readily available. So if we're just given a polynomial function like the following, how do I know what the end behaviors are simply by looking at the polynomial functions? So let's investigate what happens here. If we try to separate out each monomials, in this case the negative x to the fifth right here, the 3x cubed right here, and then the 4x, by looking at different x values, going from 1 all the way out to the positive infinity, I wanted to see what happens to the function values on those monomials alone and compare which one actually gives you the dominating power, which one actually gives you a much bigger number than the rest. Okay, so for example, when x is equal to 1, negative 1 to the fifth power is still negative 1, and 3x to the cube is 3, and a 4x is 4. So although in the beginning, 4x actually has the highest power when x is equal to 1, it might not be the same way as we increase the x value. Next, if we consider the x value of 10, then negative x to the fifth monomial has the function value of negative 100,000. The 3x cubed has 3,000 as the function value, and 4x only has 40 as its function value. Already we see a domination on the fifth degree monomial. As we increase the x value to 100, this domination becomes even more severe. Right? Clearly, 400 is significantly much less than the function value from the monomial x to the fifth. If you increase the x value to 1000, then if you actually try to put this in your calculator, it might return a symbol like the following. That's using a scientific notation here. The e plus a 15 basically just tells you there are 15 zeros attached to the -1. So this is like to say -10 to the 15th power, and that's a lot bigger than any of these numbers. Same thing, if we put in x equals 10,000, it would output -10 raised to the 20th power for the x to the 5th monomial, and 3 times 10 to the 12th on the x cubed monomial, and 40,000 on the linear term 4x. So notice the pattern here. As x goes to infinity, the 5th degree monomial eventually reaches -infinity because it is a negative sign here. On the other hand, a 3x cubed would go to positive infinity, and 4x would go to positive infinity as well, but in a very, very slow way. It's much slower than the rate at which the 5th degree monomial is going to the -infinity. If you actually combine all these things to form the polynomial f of x, you notice that the function value on the f of x is really dominated by the function value of the 5th degree monomial. They look very similar there. So what this means is you can basically ignore the behavior on the lower order terms, the 3x cubed and the 4x, and simply look at the behavior of the highest degree monomial, and it tells you the behavior of the function as x gets large in both directions. So in this case, I can safely say that the f of x approaches the -infinity because that's what happens to the monomial x to the 5th as x gets large. So in this example, to answer the question which term dominates, and it should be obvious that it's the negative x to the 5th term that dominates. And the end behavior that's displayed here is such that y goes to the -infinity as x approaches positive infinity. And that is what the negative x to the 5th term does. So in a nutshell, the end behavior of any polynomial of this form is really determined by the degree n and the sign of the leading coefficient an. So in the previous example, the degree was the 5th power, the sign of the leading term was a negative, and it has to be one of those 4 following examples here. If the polynomial has odd degree, that is when n is odd, and if the leading coefficient is positive, an example for that would be x cubed monomial, that means as x gets large, then the y value has to be large as well, which means y goes to infinity as x goes to positive infinity. If x is really large in a negative direction, that is, if you were to keep putting in negative quantities that's getting larger and larger, then because we're cubing a negative number, the result of that is also a negative number. So y value goes to the -infinity as x goes to -infinity. And it has to look like the following. Notice that I always use the arrow on both ends because we're describing end behaviors. Pattern of keep getting larger or getting smaller has to continue on as x gets larger and smaller. On the other hand, if the degree of the polynomial is odd, but the leading coefficient is negative, and a classical example of that is the polynomial -x cubed, then as x gets larger and larger in the positive direction, we would then get a negative large quantity for y because of the negative sign attached to it in the beginning. On the other hand, if x gets smaller and smaller, or it gets larger in the negative direction, then you get a negative quantity out of the x cubed term, but then when you attach negative sign in front, it turns into a positive quantity. So y gets to be positive infinity as x gets to the -infinity. And so this is just going to be a picture that's almost like a mirror image of the one we had, and just basically flipping goes like this. And that's a classical -x cubed picture. If your polynomial has odd degree, then its end behavior has to look like one of those two. On the other hand, if your polynomial has even degree, then it's going to be one of those following 2 examples. If the leading coefficient is positive, then your classical example for that will be an x squared polynomial. And as we know that if we square any real number, it's going to produce a positive quantity. So either way we go, we're going to get the end behavior toward the positive infinity in the y. And that's the classical shape of the parabola. On the other hand, this is the total opposite. The leading coefficient is negative, then the classical example is the -x squared. because squaring any real number produces a positive number, we're then attaching a negative sign in front. This will always produce a negative quantity. So this means that the y value is always going to go to negative infinity regardless which way we go in the x. And the shape of that is your classical downward facing parabola. So in a nutshell, we expect to see the end behavior of the polynomial having even degree always look like one of the following, depending on your leading coefficient being positive or negative. Let's do a quick example here to illustrate what we just talked about. We look at the polynomial here and we try to decide the end behavior of it. From our example before, we know that the dominating term, which is the leading term, is the negative x to the fifth. Because it is an odd degree in the leading term and it's a negative leading coefficient, the graph of f must look similar to the graph of negative x cubed, which is like this. All right, so this means that the end behavior for f of x is y goes to negative infinity as x goes to positive infinity, and y goes to the positive infinity as x goes to the negative infinity. Another quick example here, we have the polynomial function x to the 10th dominating here. This is a even degree with positive leading coefficient. So that means the graph of this polynomial must look similar to the graph of x squared, which looks like the following. And remember that because it's high degree, the 10th degree is actually quite high, it should be really flat near the origin. It almost looks like a U near the origin. And then with that, we know that the end behavior is that y goes to infinity as x goes to positive infinity, and y goes to infinity as x goes to negative infinity as well. Here, I want you to pause the video and try to really think about 1 and 2 here. Look at the end behaviors, try to write it down and match with one of those 4 options below, and come back for answers. For number 1, the dominating term has an odd degree with positive leading coefficient. That means its graph must look similar to the graph of x cubed, which looks like this, that extends from the first quadrant to the third quadrant. With that graph, we know that y goes to infinity as x goes to infinity, and y goes to the negative infinity as x goes to negative infinity. And that's exactly what option A says. For the second function here, we notice that this is an even degree with a negative leading coefficient. So its graph must look similar to the graph of negative x squared, which we know looks like the downward facing parabola. The end behavior on that would be y goes to negative infinity as x goes to positive infinity, and y goes to the negative infinity as x goes to the negative infinity as well. And that is exactly option D. In this example here, you're given the function negative x cubed plus x squared plus 12x. We ask you which one of the following graphs could be the graph of this polynomial function. Now take a moment and think about your answer here. The dominating term is the negative x cubed, which has a negative leading coefficient with an odd degree. So the graph of this must look like the negative x cubed, which is something that extends from the second quadrant to the fourth quadrant. But you notice that there are 2 graphs that are having this sort of end behavior, both graph B and graph D. But which one of those graphs really is the graph of the polynomial function f? Well, we really can't figure that out until we have more information about the function itself. So there's one takeaway message from this, is that the end behavior alone isn't enough to decide the shape of the polynomial. We need more information such as x-intercepts to actually help us figure out the shape of the polynomial precisely. Nevertheless, the end behavior is a great tool to help us get a sense of what the graph of the function looks like towards both ends of the x-axis.